There we go. Okay, so our practice exam, the answer key, it has sort of the key concepts. They go over the key concepts. And then it goes through common misconceptions. And then opposite that, they kind of give like the things that would clear up those misconceptions. Okay, there's a little table with that. And then finally, they have a section that says, based on your experience at the AP reading, that's the AP marking session, they call it reading, with student responses, what advice would you offer to teachers to help them improve the student performance on the exam? I think that's a key section for you to really read through, because it does things like it says, oh my gosh, the question mentions units. So do you think you should make sure that you focus on units? Yes, things like that, okay? So when you are done, you can take a read through that. If at the end of this, you're like, I don't want to keep this, you can hand it back and I can use it for future classes, okay? Maybe save like one tree out of the billions that I am now destroying. All right. Also, these people have not yet signed up for AP Classroom. Taranyu, Hannah, Sally, Samantha, Jade, Olivia, Demi, Amy, Hanno, Jofi. And how do we do that? We go to Teams. Olivia, yeah, you haven't signed up for AP Classroom. So where we go is we go. Are we supposed to? Yes.
I signed up for Classroom for bio.
Yeah, but that gives you access to the bio stuff. It does not give you access to the chem stuff. You sign up with every AP course, you join your AP Classroom for that course.
So we just use the code, right?
Yeah, so you would go here, it says join code in the Teams, the channel, and there you are. So if you want to take a minute and do that right now, if you've got your phone, why not take a moment and do that right now if you haven't already? Again, that was Taranyu, Hannah, Sally, Samantha, Jade, Olivia, Demi, Amy, Hanno, and Jofi. The other thing is payment for the workbooks. Remember that if you are an international student, you don't have to pay for it, but please let me know, because otherwise I need to let the lady in the office know so that she knows that to check your name off the list. Also, if it is a financial hardship for you and your family, also let your counselor know, and let me know as well. So again, I won't hassle you anymore. Taranyu, Hannah, Umber, Demi, Amy, Jofi. Okay, so hopefully we can get those all paid for, and that would be great.
Oh, it's join a course or exam, right?
Yeah, it says join code, and you just copy that thing, and then you click on the link, and then you put in the join code when you get there. 7J6 ML4. 7J6 ML4.
All right, I did it.
Okay, cool.
Oh, they're back to back. Oh, wow. Back to back. 8 a.m.? Are they actually at 8 a.m.?
Yes, but you have to be there at 7:30. And when they say you have to be at the exam at 7:30, they don't mean you're in the building wandering around at 7:30. They mean like in the room with all your stuff. You've peed, you've done everything you need to do. Like at 7:30, you're in that room because you need to fill things in. Yeah?
Does your brain work at 8 a.m.?
I don't know. I would spend the month before it, like doing a time zone change for myself. Do you know what I mean? Like, because I'm a little bit that way. Like I'm an overly prepared kind of person. Other people will just be like, I'll just set my alarm and off I go, right? All right. Are there any questions from last day's homework? Going once, going twice, going 3 times, sold. So we are going to be talking today more about equilibrium, and we were on page 31. So when last we left, we were looking at this equilibrium system here. H2 plus I2 gives 2HI. All of these are gases. And our stress that we were looking at was a decrease in HI. So let's start with our forward being a non-dashed line and our reverse being a dashed line, or you can do them in different colors, it's up to you. And originally we start at an initial equilibrium state. Okay, and then our stress is a decrease in the concentration of HI. How does that affect the forward rate? Stays the same. Because we haven't done anything to the concentration of reactants, so there will be no fewer collisions. How about our reverse rate? The reverse rate? You can point, you can be like either up or down or whatever. Okay. If we have less of this, will we have more collisions or fewer collisions? Fewer collisions, so the rate will be slower. So always bring it back when you're talking about rate, bring it back to collisions, okay? Less frequent collisions for the reverse reaction. So what would that look like on the graph? We're going to have a vertical line going down for our reverse rate. And then once we've done that, what should the two curves do? They should meet in the middle, and it should go steep, shallow, flat. Steep, shallow, flat. Okay, does that seem good to everyone? All right, where did we get to with that? All right. I don't know why I have another one here. No, I don't know. We'll just leave that. I think I don't know. I think I drew the shift down here, but this time I just drew it right there. And if you wanted to talk about why is the forward rate decreasing during the shift? During the shift, what is true about the two rates? What's true about the forward rate during the shift and the reverse rate during the shift? Pardon me? They are unequal. Which one is bigger? Forward rate. Okay, so you can say, during the shift, the forward rate is greater than the reverse rate. What does that tell us about concentration of reactants? During the shift? If forward rate is greater than reverse rate, what's going to happen to the concentration of reactants during the shift? It's going to decrease, yeah? Because they're being used up faster than produced. And therefore, what's going to happen to the rate as it goes on? The forward rate will decrease since there's fewer collisions. Does that make sense? Cool, cool, cool. Do we need to do it the other way for the reverse reaction, or are we good with that? We're making products faster than we are using them up. So we're going to have an increase in the concentration of products. So the reverse rate will increase. Would we like to write that down? Anyone? Yes? Okay. We might as well write it here because I'm not going to draw anything here. During the shift, we know that forward rate is greater than reverse rate. So our products are being made faster than the products are being used up. Therefore, during the shift, the concentration of the products will increase. And therefore, the reverse rate will increase, since there will be more collisions. Alrighty. Whoa, what happened? There we go. Okay, so in general, if we increase the concentration of one chemical species, that is our stress in this case, will the equilibrium shift towards or away from that increase? It will shift away from that increase. You can think about that in any way that you like to. But like I said last day, we have the little pulley method, right? I've got A in equilibrium with B. And if this is a chain, if I push up on the chain, which direction does the top part of the chain go? If I push up on the left, it's going to go across to the right. So it's going to shift towards the products. That does not mean the concentration of B goes down. In fact, it means concentration of B will increase as it shifts that way. Okay, so we're really only concerned with what the top part of the chain will do. Okay, if we decrease the concentration, the equilibrium will shift towards the decrease. So again, if we have our A in equilibrium with B, and we've got our pulley system here, then if A is decreased, that's going to pull the whole chain along, and the top part of the chain is going to be going to the left, so it will be shifting to the left towards the decrease. Okay? And you can think pushing away. So if you push up and you pull down, you push up, you push away, you pull down, you pull towards. This general principle was summarized by Monsieur Henri Louis de Le Chatelier and is known as Le Chatelier's principle. And I would like you guys to do the best you could to word Le Chatelier's principle for your neighbor. Your definition should have the words stress, shift, and minimize, and system, and equilibrium.
Oh yeah. Is this their equilibrium? That's this their
System will wait if equilibrium at stress is shifted, the system will equilibrium if the stress. Okay, if the stress at equilibrium is no, that means is what at equilibrium is stress. The shift will the stress will shift to minimize the.
Okay, what's the first word?
A system.
System. Okay, so we have a system at equilibrium is stressed. Okay, so there we are. So far, so good. The system will shift to minimize the stress. Is good?
I got like half
of it. Okay. Now, this head to tail method, that I mentioned here, it's basically just the pulley system. It's just another way of doing the pulley system. So if you write your reaction and you draw an arrow representing the increase or decrease above the species that is changing concentration, draw your shifting arrow so that it attaches to the top of the first arrow. So its head attaches to the first arrow's tail, or its tail attaches to the first arrow's head. It's going to show you're always going to have a shift away from an increase. Those are both vowels. Away from an increase, and towards a decrease. Those are both consonants. What? Oh, first tail's head. Fix. Thank you. Okay, so you draw an arrow, for example, going up, and then you say, I must attach an arrow to the top of that arrow. And if I see a head of an arrow there, it has to attach to the tail of the other arrow. Okay? And it has to go across the equilibrium sign. But if you prefer the pulley system works just as well. It'll do the same thing. Okay? Now, this other one here, we need to draw a line across our equilibrium arrow, and it needs to touch the top of the arrow. So if we are decreasing concentration of H2, now this right here is a tail. So what do we need here? We need a head of an arrow to touch that tail.
Like the big arrow overall shift.
The big arrow is the shift. All right, let's do a couple more. If we decrease I2, so we're going to put an arrow over top of I2, that because we're decreasing, it's going to be a downward arrow. Then we attach a line to the top of that across the equilibrium arrow. And we need the head and tail to touch. This is a tail, so this has to be a head, so this is our shift. Or you can be like, oh, it shifts towards a decrease. It shifts away from an increase. If we increase concentration of HI and we draw our line across the equilibrium arrow, do I want to put a head or a tail there on my shift arrow? I want a tail because I've already got a head, so my head's going to go, head of the arrow is going to go over there, so it's going to shift to the left. So I don't care which method you use to do that, just use one of them, whatever works best for you, all of them, I don't know. Now, if you are asked to explain a shift in terms of rates versus being asked to explain in terms of Le Chatelier's principle, consider the following system. We've got some NO, some H2, some N2O, and some H2O. In which direction does the equilibrium shift when some NO is added to the system? So first of all, you can just be like, okay, I can easily figure out which way it is going to shift. Wait, which way is it going to shift? It's going to shift to the right. But if we're going to explain it in terms of Le Chatelier's system, we are going to say, what is the stress? And then we're going to say, therefore, the system shifts, and you're going to give the direction. So it shifts to the right. And according to Le Chatelier wants to minimize the stress. The stress was an increase in NO, so what does the system want to do? The system wants to decrease. So it wants to use up NO and bring the concentration of NO back down. to close to its original value. So that's how you explain it in terms of Le Chatelier. When NO is added to the system, let's explain it in terms of rates. So if we add NO to the system, what is happening to our forward rate? Our forward rate is increasing and our reverse rate stays the same. So you can draw those little rate arrows for yourself to be like, the forward rate increases. And whenever we're talking about rate, bring it back to collisions. And it increases due to an increase in the number of the collisions between, you can say NO and H2, or you can just say reactant particles. What happens to the reverse rate? When we increase NO, what happens to the reverse rate? Stays the same. Because the concentration of products what did we do to the concentration of products? Nothing. It has not changed. Now you're going to compare the two rates. Since the forward rate is something than the reverse rate, since the forward rate is faster, bigger, greater, whatever you want to say, than the reverse rate, we are making what faster? Products. We're making products faster than we are using them up, which means the system is shifting
To the right.
to the right. There we go. Do you guys want to try the next one on your own? Okay. When you're done, check with your neighbor, and then you can check up here. The stress to the system was a decrease in H2. Or you could just say was decrease in H2, but like, yeah. If you were speaking, you would have an in there. Yes? In order to make the stress less, I'd like you to be specific about what stress you are making less and how you are making it less. Does that make sense? So you're making more of the H2 because the stress was a decrease in H2. Yeah? Good question. All right, now we're going to try it in terms of rates. Is okay? Okay. So what are the basic things? Tell me what, if you're explaining in terms of Le Chatelier, tell me what the stress is. Tell me which direction the equilibrium shifts. Okay. The stress is an increase or decrease in whatever. The equilibrium, therefore the equilibrium shifts to the whichever direction it does. And then tell me why, be specific, it shifts in that direction to produce more, to bring it back up, or to use up, to bring it back down. In terms of rates, if you have an increase, you're going to say there are more collisions in whatever that direction is. If there's a decrease in a concentration, you're going to say there's fewer collisions, and therefore that rate has decreased. Compare the two rates. Therefore, this rate is faster than that rate. So, either this or this, and then do the same for the reverse. Then compare the two rates. So this one's faster than that one. Usually it's better to say which one you're making faster because that's the direction you're going to be shifting. I mean, you could say we're making the other one slower, which just becomes a little, it's just not as nice to explain it that way. And that tells us the equilibrium is shifting in whatever direction it is. So I mean, you don't have to follow this exact framework, but this framework will get you full credit every time. Okay, there's some exercises here which we are not going to do. We are going to take a look now at my very favorite on page 38. Changing pressure and volume. Now, pressure and volume depends on the number of gas molecules on either side. And in fact, if the number of gas molecules on either side are the same, it turns out that pressure and volume is not actually a stress at that point, because it stresses the reverse reaction in an equal amount to the forward reaction. Okay, but we'll get there. Pressure and volume are, how are they proportional? Are they directly or inversely proportional? Inversely. As volume is decreased, pressure increases, and vice versa. So here we have a rate perspective on how shifting with pressure changes works. So what we're going to notice here is that in this equilibrium system, we have 1 and 2, we have 3 H2. So that is 4 gas molecules on the left. And over on the right, we have a 2 NH3. So there are 2 gas molecules on the right. If we decrease the volume, what happens to the pressure? Increases. If the pressure increases, what happens to the rate of the forward reaction? The rate of the forward reaction increases. Why?
There's higher pressure. There's more than anything.
Yep. Okay, there's the same number of particles in a smaller volume.
It's like another way of
Yeah.
saying that.
Yes. Pressure for gases is analogous to concentration. Analogous. You know an analogy? Okay, so what it means is that they are comparable to each other. They can stand in place of one another. You can use concentration in place of pressure and pressure in place of concentration for gases. Okay? So this is our forward rate. Forward. What happens to the reverse rate of the reaction? It will also increase for the same reason. Now, which rate increases more? Forward or reverse, and why?
Like more as in like.
As in, which one ends up faster than the other one? The forward. Why? The side with more gas molecules experiences a greater change in rate. So just like the endothermic side was more affected, the side with more gas molecules is more affected. Okay? So therefore, and we'll talk about why in a moment, but this is just the what's happening for now. Therefore, the forward rate will experience a greater increase. And that means that the equilibrium will shift to the right. In other words, away from the side, towards the side with fewer gas molecules. Why does the direction with the most gas molecules as reactants experience the greatest change. Let's think about what happens to the concentrations if we have the volume. Just cut it straight in half. So let's say we go with our reactants. If we cut the volume in half, what happens to the concentration? The concentration, it will decrease by, will it?
The concentration.
The concentration will
Stay the same.
stay the same. Okay, so I have 4 particles in 1 liter. So I have 4 molecules per liter. If I cut the volume in half, now I have 4 molecules in 0.5 liters. So what is my molecules per liter now? It's going to be 8 molecules per liter. So if I cut the volume in half, my concentration not just increases, it doubles. Now, my products, I have 2 molecules in 1 liter, and then I cut that to half a liter. So now I have 2 molecules in 0.5 liters, which is 4 molecules per liter. Okay. So here, the change was positive for, or it doesn't have to be positive for molecule. Sorry, I'm making a mess. We went from 4 to 8, so the change was 4 molecules per liter. Yeah? We went up by 4 molecules per liter. And the products went up by only 2 molecules per liter. So which one experienced the bigger change in concentration? The reactants. So we have a bigger change in concentration, and therefore the forward rate is affected more. In the reverse reaction, we have a smaller change in concentration, and therefore the reverse rate is affected less. So the forward rate increases more than the reverse rate. So both rates have increased, but since the forward rate increased more than the, I need to put a than the in there, fix. Reverse rate oh, I don't need a than the. I'm not reading my sentence. Since the forward rate increased more, no.
So the forward rate is greater than the reverse rate.
The forward rate is greater than the reverse rate. Oh my Lord. Oh, that was too hard for my poor little brain to do. Okay. Meaning we are no longer at equilibrium. Are we making products or reactants faster than using them? Products. Faster than we are using them. So the system is shifting right. Okay.
Wait, what was the last one? All right. Okay, so we're decreasing the volume, so
all the concentrations increase. But because you've got more gas molecules on the one side, you've got more of an effect on the concentration because each of those concentrations doubles
if you decrease the volume.
if you decrease the volume.
Does it have to do with anything like the frequency, right?
The frequency of collisions? Yes, because if you have a bigger increase in concentration, you're going to have a bigger increase in the number of collisions.
Oh.
Yeah? Okay, if you prefer a less visual and more mathematical representation, if you start with 4 gas molecules per unit volume and 2 gas molecules per unit volume, and then you cut the volume in half, you finish with 8 and 4. So the change in gas molecules per volume is 4 for the reactants and only 2 for the products. So you have a greater change in concentration for the reactants than you do for the products. And a greater change in concentration means a greater change in the number of collisions. So the greater amount of gas molecules on a side causes a greater change in concentration when a volume is changed, which means a greater change in that particular rate. Okay, so you can remember the side with the greater number of gas molecules has a greater change in rate. Therefore, in this particular case, the forward rate is increased more. So if we fill in the arrows, we could say originally we were at equilibrium. And then we decreased our volume. The forward rate speeded up a lot, and the reverse rate speeded up some. So our forward rate is greater than the reverse rate. So we are making products faster than we are using them. Therefore, we are shifting to the right. Is good? Okay. Probably you're not going to have to explain shifting in terms of rates with a gas because it's just lots of words. I've never seen one on AP, and I don't like marking that many words. So, you know, take that as you will. Okay. What happens when we decrease the volume? Let's graph it this time. What happens when we decrease the volume of this system? We're going to start with our rate diagram. So I would like you guys to label your axes, and then we'll do the rest of it together.
Do we also write liters and cycles every rate?
No, just write rate. So the stress is a decrease in volume. What happens to our forward rate when we decrease the volume? It gets faster. There we go. What happens to our reverse rate when we decrease the volume? It gets... Does it decrease the reverse rate? I've squished the whole thing. Everything's in a smaller space, so everything is going to have more collisions. So we can't be decreasing any rates because everything is in a smaller space. Every rate is increasing. The only question is the reverse rate increasing the same amount, more, or less than the forward rate? We've got 4 gas molecules here, and we have 2 gas molecules here. Sorry? Yeah, the reverse rate is increased less because it has less gas molecules. Okay? So up it goes, but not as much. What will we now do? I'm going to make that a little bigger to make my drawing easier. What will we now do with our 2 rates? Make them meet in the middle. And remember, you're going to go steep, shallow, flat, and steep, shallow, flat. Okay? So that's a rate diagram for that particular reaction. Concentration diagram for that same reaction. Concentration goes here. Time goes on that. Whoa. Ah, where did everything go? Okay, here we are back in business. Time goes on the x-axis. We are going to arbitrarily put N2, H2, and NH3. And this is where, honestly, these diagrams become very, very inaccurate. You thought they were inaccurate to start with. Now they get really inaccurate, because if I were to, say, cut the volume in half, right? If I decrease the volume, every single one of those would double in concentration, yes? So I would actually be like, oh, this one has to go up to here, and then this one has to go up to here, and then this one has to go up to... Do you see the problem? Do you see how we're now running out of graph? So we're just going to say, okay, we don't care by how much they actually go up. What we do care is that they all go up because we squished the container. And we're just going to draw them all the same because that makes our life easy and tidy. Now remember, which way are we shifting?
Right.
We are shifting to the right. So what should be happening to our concentration of N2? N2 should be decreasing. Oh, but it's got a coefficient of 1, so I'm going to try and make that one the smallest one. Okay, I don't want to make it too big, otherwise other things are going to go crazy. So I'm going to make it go down by a certain amount. There we go. H2 is going to go... It's going to go down, but it's going to go down by how many times as much?
3 times.
3 times as much. So I got to go like down 1, 2, 3. So I'm going to end up about here. Ish. And then for my NH3, maybe I'll do it in red so I can see it a little bit better. Yes.
I thought we weren't allowed to pass like the bottom one.
That's when you're changing a concentration. When you're changing the whole volume, those rules go out the window. Okay? Because now you've got all sorts of things affecting each other. And like I said, these diagrams are not particularly accurate, so let's not get, especially the pressure volume ones. NH3 is now going to go up by 2. So it should end up about 1, 2, about here. And I'm glad I drew that one in red, because then you can see the difference between the stress and the shift. Right? But because it went up to start with, it then carries on going up because we are also shifting in that direction. So that was a rate perspective on why it shifts. Notice that all the concentrations in volume, they all change in the same direction in response to the stress, due to the stress, increase in volume, decrease in volume. Sorry. Although in an ideal world, the concentration changes would be proportional to the coefficients, but we would often run out of space and it would get ugly. So we usually just make all the concentrations go up by the same amount, okay? Or a similar amount. The shifts, the changes due to shifts should be proportional to the coefficients. Okay. Ooh, we have a little simulator here, which I will let you play with at home, maybe. Let's see. Can I get it up and running? javalab.org. Okay, let's see. Where did I put my mouse? Where are you? Oh, there you are. 2.2C. Dropbox.
Yeah, it's on Monday. I thought it would be like the last one.
Gesundheit. Okay, here we are. Here is, let's try, can I make it bigger? There we go. Let's try compressing.
Oh, wow.
Which way did we shift? What have we got all in there now?
Molecule.
What kind of molecules? Are those NO2s or are those N2O4s? Those are N2O4s because we shifted in the direction of the smaller number of particles. Oh, what just happened? We got two NO2s. They should be switching up partners, but apparently they're not doing that. Maybe they will. Will they? No. It's not that sophisticated. Okay, let's make it a little bigger.
There's more?
More. Do you see how it's trying to keep the pressure the same? By now it's throwing in more molecules. Okay, and by trying, this is the Le Chatelier non-explanation, you know. It's like we start with a fairly high pressure, right? And then the pressure is going to decrease. So what happens? We make more particles to fill that space and make the pressure higher.
Why is there so many lines?
Okay, and again, as we decrease the pressure, the system says, oh, I need more molecules to fill that space, and so it makes more molecules, and it keeps trying to fill the space by making more molecules, but eventually it can't, you know, keep up with it. Yeah?
So they just kind of like divide.
Yeah, and then when we make it smaller again, it says, oh, I need the pressure to become smaller because I'm making the pressure bigger. So now it switches to the fewer molecules to make the pressure smaller. So we increase the pressure, it tries to decrease the pressure by making fewer molecules. Is good? Okay, I don't know why we have 2 of these. What's the point? I guess so you can see different mixtures at the same time. But anyway, there we go. All right. So you can see here, I've done the same thing, kind of. We've got our initial volume, which has an initial pressure. We decrease the volume, which increases the pressure, and then it shifts so that there's fewer molecules altogether, so that the pressure goes back down. So this is Le Chatelier. Le Chatelier says, my stress, remember, you're going to say, oh, and this is, I should be back over here, not on that one. The stress, remember when you're talking about Le Chatelier, you start by saying, what was my stress? And then you say which direction the system shifts. So the stress was an increase in pressure. So therefore, the system is going to shift to the side with fewer gas molecules. In other words, in this particular case, B, side B, has fewer molecules. We've got 2 A's and 1 B. In other words, to the right, the smaller total moles will bring the pressure back down. Fewer gas molecules means fewer collisions with the sides of the container, and therefore the pressure will decrease. Ooh, let's write Le Chatelier's principle once more while we're here. What words do we need in here? Stress, equilibrium, system, shift, minimize, and maybe that's it. I think that's it. Okay, go for it. I think so. Okay, I got this. If A, I was right. The system at that. No, the system at equilibrium. Is stressed or stressed? Stressed. Shit. Systems. Oh, bullshit. No, woman. Oh, woman. So, I was right. Bullshit. Bullshit. Minimize. Exactly. Okay. Whew. All right. This one just shows you Le Chatelier's principle for when we increase volume. Do you see how all of a sudden we've got more space in here? The pressure is lower. And if the pressure is lower, the system wants to make the pressure.
Greater.
If we made the pressure lower, the system wants to make the pressure
Greater.
higher. So which side are we going to shift to? Fewer or more gas molecules? More. We're going to shift to the side with more gas molecules. Okay, so there we go. The stress was a decrease in pressure. The system shifts to the side with more gas molecules. In other words, in this particular case, that would be to the left. The greater total number of moles of gas will bring the pressure back up. And if we have more gas molecules, that means we have more collisions with the sides of the container, which means the pressure increases. Okay, very nice. Whew. I don't want to do this right now. We can come back to this later, yes? Yeah? Let's go to changing temperature, page 50. We got a reaction here. Page 50. N2 plus 3H2 gives 2NH3 plus 92.4 kilojoules. Is the forward reaction endo or exothermic? Exothermic. It is releasing energy. And that would mean that the reverse reaction is endothermic. Which reaction has the higher activation energy? Reverse, because the endothermic reaction always has the higher activation energy. Yes? Okay. What happens to the forward rate when the temperature is increased?
It will increase.
Forward rate increases because increased frequency of collisions plus increased percent of successful collisions. And this is all because KE increases. What happens to the reverse rate when the temperature is increased? It increases, yes. Why? Because same as above. Which rate is increased more? Oh, I do have a diagram. There we go. The activation energy of the, hang on. Oh, there we go. Yeah, because we got both of them. Which one is the higher one, the bigger one? Endo. So this is our endothermic reaction. Our EA of the exothermic reaction is this one here on the bottom graph. And so what we're going to do is we're going to look at our percent of collisions. The endothermic direction is the reverse direction, and this is our forward direction. So we go from having this many effective collisions, which is about, and you'll have to trust me on this, I went through and put little triangles all over this dang thing, and it ended up being about that's about 1/25th of the cold sample, okay? That little black shaded section is about 1/25th of the cold sample. In other words, about 4%, okay? The warmer sample, we've got all of this. And that is about 50% of the warmer sample has enough energy to react. So in other words, the warmer sample these are effective collisions. And if we take 50 and we divide by 4, the warmer sample is going to be about 12.5 times faster, because 12.5 times as many collisions will be effective. Does this make sense so far? Okay, now we're going to look at the exothermic reaction, which is our forward reaction. And we have, because it's exothermic, the EA is smaller. All right, and if we look at our colder sample, that is about 25%. Okay? So we have, in our colder sample, we have 25% effective collisions. And in the warmer sample, we have about 2/3, or 67% effective collisions. So if we take the warmer and we put it over the colder, the warmer sample is only about 2.7 times faster. So the lower the activation energy, the less difference a change in temperature makes, right? And exothermics always have a lower activation energy, so they are affected less by a temperature change. Okay? You're never going to have to draw these diagrams. You're never going to have to come up with these fractions. This is just to make you feel better about the fact that endothermic reactions are affected by temperature more. Their rates are affected by temperature more. Okay? It's to make you feel good about that, not for you to reproduce this in any way, shape, or form. Okay? And if you don't feel good about it, you can be like, I'm just going to remember endothermic rates are affected more, and that will do you. That's all you need. All right, changing temperature affects the rate of the endothermic reaction more. So after increasing temperature, which rate is going to be faster, the forward or the reverse, and why? The reverse is going to be what? Oh, yeah, you're right. You're right. I'm reading it backwards. Yeah, because this is endo. Endo increases more. And we have our exo, which increases less. So the reverse is faster. You're never going to have to explain this, like blah, 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 blah. So we're just going to say the reverse is faster, and we're going to use our arrows with endo increases more and exo increases less. So what is being made faster, reactants or products? Reactants. And therefore the system is shifting to the left. So we're going to do a rate diagram now, but we're not, because like class is ending in 1 minute. Your homework You've got the practice exam, but that's only 1 hour. You should probably spend in the neighborhood of another hour going over the answer key. So that's like 2 hours of chemistry this weekend. What? That's like nothing. University, it's like 3 hours per day. Okay.
She's like, nobody will prepare you for it.
And how about you do page 35, 36
In the pink book?
in the pink book?
Catherine's dying.
Hi, yeah.
Isn't like the Josh always
Yeah, cherish your senior. And I was like, bro,
Just
senior
like a
year,
example.
right on this.
This is just an
She's like,
example.
yeah.
Yeah.
Imagine that time 10. She was late for her lecture. And then she brought me out this cash for the law. Kicked her out because they were closing, but they had to finish the project or whatever. And then she's like, you have to run